Part 3 of our exam starts off in numeric response question number 5. Says, electrons can produce gravity, electric, and magnetic fields as a result of the following properties: charge, mass, and speed. We want to match the electron properties with the field that they produce. Well, mass produces gravity, so we're going to say the first one is 2. We know that charge produces an electric field. We're going to say that's 1. We're going to say that charge produces a magnetic field as well, but not just a charge, because a charge by itself doesn't produce a magnetic field. A charge that's moving produces a magnetic field. So we're going to say 2 goes with gravity, 1 goes with the electric field, and 1 and 3 together go with the magnetic field. Okay, you couldn't just say 2, 1, 1. You have to have the charge moving to produce the magnetic field, but you don't have to have it moving to produce the electric field. An electromagnetic wave is produced by an accelerating electric charge, not by a moving charge, but by an accelerating electric charge, D. Speed of light. Hey, here's some things you got to read through and see which one is the best way to measure the speed of light. Observe the time delay for an eclipse of a moon of Jupiter. What? Observe the time delay between uncovering a light on one mountain and having an observer on another mountain. That was Galileo's experiment, right? And this was terrible. The interference pattern produced by a single source that emits light that travels slightly different but precisely measured distance. This is the double slit experiment. Okay, this is the interference pattern: bright spot, dark spot, bright spot, dark spot. And we actually get really good. We get really good results from that. So this is good. In fact, it's real good, not just good. What about that other one, though? Observe the time delay for an eclipse of moon of Jupiter. What? Well, if we say that this one is the best one and this one is the worst one, then it's got to be 2, 1, 3. Why would the first one be somewhere in the middle? Okay. In the end, if you measure a time delay when you uncover lanterns on one hill and another hill, the reaction time is so big compared to the time that it takes the light to travel, it's going to give you terrible results. If you increase the distance pretty dramatically, like we're talking about the distance from here to Jupiter, well, then all of a sudden reaction time isn't nearly as big, right? But light still travels pretty quickly from here to Jupiter. Okay, so it's still an issue. The double slit experiment, Young's double slit experiment, the whole interference thing, that's by far the most accurate one. That's why we spent so much time on that. Now, another accurate one, pretty accurate one, was the Michelson experiment, right? Okay. And that's the next question that we have, question number 20. Eight-sided mirror. This is your type of questions, you say? Okay, the good news is there's a very good chance we're going to see something like this on the exam. Right? A very good chance. We're going to say, look, we got 2 equations, V equals D over T, T equals 1 over F. We're trying to find, we got a speed. We're going to say it's 3 times 10 to the 8, the accepted speed of light. The distance is 70 kilometers or 70,000 meters. Don't know what little t is? Let's find it. Little t, the time for 1/8 of a rotation is 2.33 times 10 to the negative 4 seconds. Let's multiply that by 8 to get big T. Gives me 0.0018667 seconds. And then let's find the frequency by saying 1 over that number. Going back to this equation, right? We do that, works out to be A. Hey, if I had to guess on this, why would I have guessed A? As I've mentioned to you guys a whole bunch of times this past semester, you should usually expect to get a number in this range for this one or another. And that's hard to remember all of those little things, right? Okay. I told you, like Young's double slit experiment, probably 10 to the minus 7 meters for a wavelength. trying to find the speed of a charged particle, probably 10 to the 5, 10 to the 6 meters per second. You're doing a Michelson experiment, probably 10 to the 2 hertz. Okay, I'll forgive you if you don't remember all of those little things, because it's hard to remember all those little things. But if you do, okay, we're usually in that range of 5, 6, 700 hertz here, and that's right in there, 10 to the 2 hertz. #21. Question says, when white light from sun strikes a flint glass bead, the white light is separated into its component colors, 2 of which are illustrated in the diagram below. So we got white light coming in. Can't see it very well in this diagram, but you can in your photocopy, where it's refracting, right? The white light is splitting up right here. It's refracting, and then it reflects like this, and we get violet light coming out here, and we get red light coming out here. Now, in the end, what's causing that? Okay, what's causing it? Well, it's the different index of refraction between red light and violet light, right? It's called dispersion. We know that this flint glass will have 1 index of refraction for violet, 1 index of refraction for red light. If we think back to the prism that we drew on the very first day of refraction, it's also on the cover of the Pink Floyd album, we got red and violet down here. There is the smallest index of refraction for red, and we got the biggest index of refraction for violet, because violet bends more. All right, let's read through our options here. The index of refraction of red is greater than that of violet. No, look, we just said, by thinking back to the very first diagram we drew for refraction and dispersion, we just said that the index of refraction for red is smaller. B, the index of refraction of red light is less than that of violet light. All right, that seems to work. C, the index of refraction of violet light is greater. Okay, that might seem to work. D, the index of refraction of violet light is less. No, that doesn't work, because we know it's more. So which is it, B or C? That's what it boiled down to for me when I was doing this question for the first time, and I probably spent 2 or 3 minutes looking at it. What's the difference? They look the same to me. What is the difference between those 2 options? It's a small, subtle difference. 1 word. Yeah. Yeah, it's refracts versus reflects. Okay, this reflection over here has nothing to do with it. It's the refraction rate here and the refraction rate here that has everything to do with it. So the answer is going to be B for us. 7. On a particular day, the index of refraction of a 5 megahertz radio station is 1.81. What's the critical angle? Here's my frequency. Here's my index of refraction. We're going to say that the speed of light is 3 times 10 to the 8 meters per second in a vacuum. Let's say that the critical angle is, let's use Snell's law here. For sine theta 1 over sine theta 2 equals n2 over n1. Let's say sine theta c over sine 90, because when we're finding the critical angle, theta 2 will always be 90. Hey, what do you think the odds of having a single problem involving a critical angle is on the exam? I'd say pretty big. Yeah, I'd say pretty high. No. If you go back to the diagram here, we're always going like this from a high to a low index of refraction. Okay, this would be theta 1, this would be theta 2. In order for total internal reflection to occur, theta 1 has to be a certain value, and theta 2 has to be 90 degrees. So we're going to say sine theta 1 over sine 90, and sine 90 is 1 equals n2 over n1. So really we're saying theta c is equal to the inverse sine of n2 over n1. N2, what's n2 here going to be? Going from high to low. So we're going to go from 1.81 to 1.00. That's the error. If you get those two mixed up, though, you get an error on your calculator, right? Do the math here the proper way, and you end up getting 33.5 degrees, and that seems like a pretty reasonable number. This is one where you have to enter the decimal place in your numeric response sheet. Hey, when I did this test for the first time, I got 49 out of 50. I got 98%. I probably wouldn't have got 98% if I was in grade 12, because I wasn't nearly that smart in grade 12. I got 98% after having done physics 30 a million times. You do physics 30 a million times, you'll probably get 98 too. This is the question I got wrong. Shouldn't be that hard. Where do you think my mistake was? I was careless. And it tells me the distance from the focal point to the object is 2.4 centimeters. What did I make that? I made that my object distance. I said DO is 2.4. It's not. DO is 2.4 plus 4.3. It's going to be 6.7 centimeters. Does that make sense? It tells me this is 2.4, tells me this is 4.3. The total object distance is 6.7 centimeters. That was my mistake. And you know what happened when I said DO was 2.4? I got an answer that was up there. Those dirty, you know what's. Dare they do that to us, eh? Look, we got, I don't remember to be honest, Rucker, but probably was. We got DO. We got the focal length is 4.3 centimeters. Pretty easy question now, right? 1 over F is equal to 1 over DO plus 1 over DI. 1 over 4.3 equals 1 over 6.7 plus 1 over DI. So pay attention to little things like that. Let's go through this here just to make sure you guys can do it. Let's say 4.3, x to the minus 1. Subtract 6.7, x to the minus 1. Let's flip that over. And look at that, you get 12. And the answer is D12. Four more questions, man, 4 more questions. Then we'll take a break for a sec. Student follows 3 procedures to study properties of laser light. She uses a laser that emits monochromatic light, one color. We like one color, although you guys know how to deal with more than one color, right? If it's a diffraction experiment, what do you do if it's more than one color? Pick a color, right? You guys had a question on your unit test involving multiple colors, and how many of you guys messed up on that because you looked at red and green and blue and all these different colors and said, oh, which ones, you know, each of them is a maximum. Well, they are each a maximum, but they're all the first order maximum. There is a spectrum of all of those in the first order and the second order. So basically what you do is delete all the other colors. If you're dealing with yellow light, pretend the others don't exist. You know what though, when they tell us it's monochromatic, I don't know, it just seems to make it easier. Here's our wavelength. We don't like nanometers, but that's our wavelength. We got 3 procedures, 3 observations. Hey, you want to find the energy of one photon? It's just hc over lambda. Hey, don't overanalyze something like that. Hc over lambda gives me 3.14 times 10 to the negative 19 joules. In procedure 1, the wavelength of the laser light in the crystal is what? Procedure 1, the wavelength is what? Well, in procedure 1, what's the best way to do that? Procedure 1, we know the index of refraction is 1.53. We know the speed of light is 3 times 10 to the 8. You can find V. Get the value for V. I don't know that's the best way to do it, actually. You know what? I think there's a better way to do that. Is that valid, guys? Have I done anything wrong on that? Not at all. Yeah, I'm not sure it's the best way to go, though. Let's try this another way. Let's say lambda 1 over lambda 2, Snell's law, equals N2 over N1. Let's assume that we're going from air to this crystal. We got the we got the wavelength in air. Looking for the wavelength in crystal. The index of refraction of crystal is 1.53. The index of refraction of air is 1.00. So that's the way we're going to go. And it works out to be, by the way, 4.14 times 10 to the minus 7. That's going to give us either A or B, right? A or B. The speed of laser light in the crystal is less than that of air, and always slows down when it goes to something other than air, unless it's a vacuum. Question 8, in procedure 2, the angle between the central max and the first bright spot. We're going to say n is equal to 1 there, right? We're looking for theta. Central max and the first bright spot. Listen, here's 1 over d, right? Not d, but 1 over d. So we find d there, flip it over, 2 times 10 to the minus 6. We're looking for theta here, so let's plug in some numbers here. Let's say lambda times n over d equals sine theta, or theta is equal to the inverse sine of lambda n over d. So we got everything here now, right, guys? We just had to remember that those lines per meter wasn't d, it's 1 over d. Do the math there, works out to be 18.5 degrees. Good thing we were able to use that equation, because that other one wouldn't have been valid, right? xd over n times L isn't a valid equation for this, because the angle is bigger than 10. In order to produce an electric current in procedure 3, the student must use radiation that has a blank wavelength. Okay, so we want to have a current. We want to produce a current. If we want to do that, we need either a higher frequency or a, who knows the answer to this, higher frequency or a smaller wavelength, right? Remember, it's min frequency, threshold frequency, max wavelength. So you want to be above the frequency, you want to be below a certain wavelength. And you probably want to have a smaller work function, right? If you zap up the energy of the photon and you amp down the work function of the material, then you're going to maximize the possibility of ejecting an electron, right? So the answer is going to be C for that one.